done till now, we have discussed the motivation of doing StatMath. I explained to you this is two parallel framework of theoretical science, entire theoretical science as we apply condensed matter to physics and chemistry or even gas phase, biology and material science included. There are only two theoretical frameworks and they parallel. Often they are interacting among themselves. One is the quantum mechanics that you have studied and that evolved from spectroscopy, almost entirely to spectroscopy of different forms. And then the statistical mechanics, which started essentially with Maxwell and then Boltzmann and Willett-Gibbs, and that the two desire, the two things that motivated these people. One is the transport properties and the kinetic theory of gases, other is the thermodynamics. So as I explained to you, thermodynamics has the limitation is that thermodynamics cannot calculate anything by itself. At most, you can calculate with certain drawbacks through specific heat by integrating step by step. That is why Planck and Nernst introduced the third law, which all of you know is an imperfect law, but that was introduced to give a reference that we needed a place to start and where entropy is zero, and that allows us to integrate. So thermodynamics and kinetic theory of gases, two things. One is an equilibrium, the phase transitions, free energy, and all this stuff, and the other is the transport properties, which is the way to calculate or attempt to calculate things like not only specific heat, because first calculation of Maxwell-Boltzmann was specific heat came from kinetic theory of gases, and you all of you know 3/2R, right? Kinetic theory, specific heat, and also viscosity, all these important things. Historically, while statistical mechanics was being developed, there is another branch of science which played a very, very important role, and that is hydrodynamics. Hydrodynamics is the one we physical chemists or chemists don't study at all, but it's a very formidable to the extent there are departments where in mathematics, and physics, a good number of people work on. Have you heard of the recent thing called active matter? The new things, the white bars, the new development that has happened in physics, that why bars flock, they move together, why fishes. There's a beautiful area that has come up, really beautiful area, and many of my colleagues are vigorously working on that and are doing good work. But that essentially is a kind of extension of hydrodynamics. So statistical mechanics and hydrodynamics kind of came together. Hydrodynamics and statistical mechanics came together many, many times. So 19th century saw a lot of development of hydrodynamics historically. And the people who are working on StatMath, statistical mechanics, little did they know that these two will merge. And they did merge eventually around 1970 to develop even more powerful formalism. The historical aspects of statistical mechanics is as interesting as of of quantum mechanics, and we have not really chronicled it well. And in this country, there is an emphasis on quantum mechanics and quantum chemistry, which is certainly well placed, and nothing against that. But that kind of seems to be ignoring the StatMath, huge field of StatMath. And I told you in a major American university like Harvard, UCLA, Chicago, if there are 5 theoreticians, the time I did PhD, 4 of them were doing StatMath, statistical mechanics. The reason is that even polymer, whole of biology, are essentially purview of statistical mechanics. That's the reason. Now we have discussed how Boltzmann tried, motivated by Maxwell, couldn't go very far because he tried to do the full time dependent statistical mechanics, and things are correlated. The reason we exist, I speak here in front of you, you see it and hopefully listening, and your mobile, everything here, because particles interact. Proteins fold, DNA is producing your enzymes, and your enzyme, right now you guys have coffee, probably have coffee, and there is the lactose there is broken up by beta galactosidase. That enzyme tirelessly doing work in your body. These are all is explained and being attempted to explain through statistical mechanics, with whenever necessary input from experiments and quantum mechanics. So when Boltzmann tried to do all these, he didn't know all these things, but of course he tried to do full time-dependent statistical mechanics, taking a clue from Maxwell. And Maxwell introduced the concept of probability distribution of velocity, the famous Maxwell distribution. So he tried to develop, and he couldn't do it, he couldn't go very far, it was too complicated. But his attempt gave rise to many things, including entropy equal to K, L, and omega. That's a wonderful equation, which is the most important equation of statistical mechanics, and where everything step back starts. So, and I told you, we still don't know many things. We still don't know why the value of Boltzmann constant is 1.38 into minus 16 arcs. Right? Now I discussed, there is a tentative derivation. I still consider better to, if you don't do Boltzmann's original derivation, which is complicated and time-dependent stat mech, where this function first came, I would rather take it as an unsatz, the postulate along with the rest of the things. If you want that distribution, we can do that. A is equal to minus KB sum over J, Pj, ln Pj, and Pj now is the probability of being in a microscopic state of the system. And as I told you, each system is a macroscopic system. There has Avogadro number of molecules. They are rotating, they are translating, they are vibrating. So they have a huge, far more than Avogadro number of microscopic states. This is really amazing and mind-boggling. That there's a calculation given in Macquarie, 1 cc, I think, of water or something here's the tentative calculation is 10. I have given also in my book 10 to the power 33 microscopic states. So huge number of microscopic states, and then microcanonical ensemble is the ensemble, that is NVE ensemble, and that ensemble is constant energy, constant V, constant number. So number of particles in the system is constant and kept fixed. Total volume in the system, we put it in a box and keep it fixed, and then E is the energy which is fixed. It's not interacting. We also call it an isolated system. And in that system, then one makes the assumption, gives. I mean, the assumption there is microscopic state is equally likely. There was nothing much he could do actually, because we don't have much of any information. On that is an isolated system, so we said, okay, of course he knew the Boltzmann distribution. So each state is equally likely. If each state is equally likely, then Pj is 1 over omega. Then 1 over omega, minus becomes plus, and everything 1 over omega, and this gives an omega, because this gives the omega cancels, and you get this. I'll take that proof with a bit of salt, and I gather what it is from directly. Okay. But this also, nothing wrong with this derivation. It's perfectly okay. Now, now what we did next in the we went to Euler equation of thermodynamics, and we got a differential of ds, and with by varying N, V, and E, and then we get. I hope I'll be able to get that. Yeah. So we go to Euler equation, and we have this. The 2 pointers in 4 days. I managed to lose 2 of those things. That's my students' claim. I claim they have lost it, but since I have a proven track record of losing things, I guess I cannot argue too vociferously. Okay, and I don't have that, so I have to do this. They told me that's the punishment. Now, so this I do ds. So this is written like that. This is the famous Euler equation. Then all of you know. And one thing that we have done a number of times. I did thermodynamics first year BSc, second year BSc, because one presidency college was closed by Naxal movement our time. So one person taught us, was very good actually. Then the real professor who was supposed to teach is a very famous distinguished physical chemist, Professor May Chaudhary, died last year, a year before. We were very fond of him, and he then taught. Then we are taught by another person in 3rd year. Then we are taught in first year MSc, a little bit in 2nd year MSc, and then when I went down to PhD, then whole semester came 201. I'm talking SS 202 course I used to teach here. So 5 or 6 times. So you guys must be knowing this. And as a result of so much thermodynamics, I'm really able to go with thermodynamics. Okay. So this all of we accept because it's NV ensemble, so we can change COAs, and we use the Euler equation. And then important thing, what is beauty is that using the Maxwell's and all these cycling. Oh, how will you get that? Pointer will work. Okay, thank you. Very good. So then, kind of thin though. I had a large red thing. Okay, this will not work. Okay. So then we do where it is kind of limping this thing. Then we get so compare with this thing, we get this beautiful relation in the microcanonical ensemble. The temperature is so this is a microscopic derivation of temperature, microscopic definition of temperature. The number of microscopic states, you take log of that and take it, now you increase, incremental increase in energy of the system, my NVE here, incremental change, they take the derivative, I get temperature. This is an amazing relation actually, really amazing. And then you get a pressure, this we actually use a lot in this particular quantity. And then you get the chemical potential. You know, yeah, there are many lot of very nice comments one can make about it. Some of that I made, but there are many other is given in the book, so you better look at the book. So now, this is a brief review of the microcanonical ensemble. Now we'll go to canonical ensemble, which, as I already remarked at least twice, that is the most important ensemble for theoretical studies and many other things. So, canonical ensemble. Canonical is the one, you know, is a canonical example. Canonical means something which is a common or representative of something. So canonical ensemble is this ensemble where now we allow, see, one of the problems with the isolated system is that this is, however wonderful and beautiful it is, and simulation we many of the time use the microcanonical ensemble. So at one time microcanonical ensemble was not considered very useful other than formal derivations, but now the thing has changed in the last 30-40 years because of computer simulation, that people, really Puritan people, they like microcanonical ensemble because, you know, if what you do, everything is exact. Canonical ensemble, which, but the real systems unfortunately is the where you had exchanging energy, like a body or you do an experiment. Then we, much of the time we have NPT, If n goes out, mu pt, but we'll come to that later. We'll do one at a time. So now we allow my isolated system to exchange energy with the surroundings. So each particle now has the same number of each system of my canonical ensemble. So canonical ensemble is made of huge number, trillions and trillions of systems, which are all of them are NVT, like this is shown here. I recommend that you read a lot of discussion here of many things, which I'm not going to tell you. You can read it easily. So these the other book that you can see where this discussion motivated from by the book by Terrell Hill. He has two books. The one that I recommend is the Statistical Thermodynamics. There is a paperback. And this is a good book. Prentice Hall, 1950s. First edition. He has the advanced book. Don't go for the advanced book. Go for the book, premium book. So to say that we first form an ensemble. How do we form an ensemble? We take trillions and trillions of systems. Each system of so I really have one system that I want to study, and that system has, this is my system I'm going to study. I'm going to study properties of this system. That system is quasi-isolated, that has N, V fixed and T fixed. This is my system. Now how do I want to study this system? What are the properties of this system? What I do, I follow Gibbs procedure. I make an ensemble now. Okay? And that ensemble is now so many mental replica of NVT. So they are identical. My drawing doesn't say that, but they are identical. And now, but all of them have different energy. As I said, trillions of them. Now, how do I guarantee that they have the same temperature, although their energy is different? We put it in a bath. And now, the way the Gibbs constructed it, he put a large number or this huge number of these systems in contact with each other. They can exchange energy. And then he put the whole thing in a bath, and insulated it. Now I have all of them. Now I have a super system. So I have an ensemble. So my system become an ensemble. Now I pick ensemble of that ensemble. So I call that a super ensemble. Okay. Why? Because I have to go back to microcanonical ensemble. My postulates, my everything starts from microcanonical ensemble. So I construct now a super ensemble, which is a microcanonical super ensemble. So now I am going to do that these things, and there are some examples here given. So what is there? That all of them different, there, that, and then now what is the difference between microcanonical? The difference between microcanonical is here. See, I did this example before in microcanonical. We had only 4 states. We had only 4 states. The reason is that our energy was fixed. We said given a total energy 8, 4 states between 0 to 4. How many ways I can? There are 4. Now I allow energy to be different, and if I energy to be different, then so this is the one example here. So if energy is 6, then I have this many. Energy is 8, the one that we did before, that this old one. Now, so my energy can now fluctuate, and energy can fluctuate. I have additional number of microscopic states which are occupied. The system with a canonical ensemble has all these extra energy levels accessible to it, because it can exchange energy, it can change the energy. So now, so system is much richer because it can exchange energy and information and energetic. So now we have to do the calculation with these. We have to do the calculation on that. Okay. So as I told, the notation that I introduced in my last lecture, this is a very nice derivation. The best place again to look at it, probably there's a book by Mayer and Mayer which also does that. So now I introduce, so this is my system. Now total number of systems I have is NT. So T is total number of systems. Okay. Now we have to this distribution that I have talked here. This thing, how many particles given an energy? Very carefully now listen. How many such systems I have? So what I am going to do, talk of a distribution. So my systems are distributed in the energy, and that energy 8 has 4 systems. This energy 10 has 2 systems. So now I introduce an index J. Now I introduce the index J. J, that I say that Nj, the Nj is the number of systems, like particles, number of particles, but number of systems in energy level J. Now, this energy level J, which is Ej, Nj Ej is the total energy of the system. Is it clear?
Small.
I just told that. Okay. Let me write down. My students told me that I have to be more explicit because these days students are used to very explicit things. Okay. Nj is the number of systems in energy level okay, right? So what we are doing now, I told you this is a little elaborate derivation, but bear with me. So we have formed a super ensemble. I am formed a system. That system is now it can exchange energy with the particles, and in my ensemble, in my system, my large system or super system is made of putting all the canonical systems together to form a microcanonical super system. So I am going one step up, and I'm going to come one step down. Okay. So it is going up and down in order to go to my make connection with the microcanonical, where I can say each state is equally likely. Otherwise, I cannot do that. Now, in my super system, I have large number of systems. and then I make all the super system together and make a super ensemble. Okay, so in my super system, I have distribution of the system in different energy levels. So systems are now distributed. So in the super system, which is a huge number of systems, they can have different energies. So I can consider a distribution now that my systems, in the number of systems in energy level Ej. Is that okay? It will abstract. And however, I have put all them together. I have constructed super system which is a microdynamical. That energy is now constant. Okay. So now I say my n number of systems in the energy level Ej, I have to add up all the J and I get the total energy, which is fixed. Now tell me one of you should be able to tell me what I am trying to do now. What is the most important thing that I am trying to calculate at the end of all these things?
The distribution of energy within the system.
Absolutely. You guys know this? Who did it? Raise hand. How many people have done that? But whoever said that, without knowing if he said that, that's a very clever. Okay, so we need to go to that distribution. Probably you guys also did probability theory because this is not it. So the whole idea now is to get this distribution, Nj. So we are going to go this distribution. How do we do it? And what is the procedure? I told you the only procedure that we have is go to microcanonical ensemble. And the microcanonical ensemble, what do? We now go, I'm using that. We go back to Boltzmann. And we say omega equal to okay? Just a multiple here. This you guys are beginning to take in your class 11. But however, there is a difficulty here, which is that the AI have these things that I have to evaluate. I take log of that, and that is it is a function which has to be this has to be maximized. I told you that whole formulation of statistical mechanics, every ensemble will have a quantity which will maximize or will find the extremum. In the canonical ensemble, this will turn out to be the Helmholtz free energy. Actually, minus of Helmholtz free energy. That's why we call Helmholtz free energy is minimum. That comes from these things. The Helmholtz free energy has to minimum comes from these things. Similarly, Gibbs free energy minimum comes also from your relevant partition function. The relevant quantity has to be maximum. So entropy is the and we call these as the partition function, and the related quantity we call the thermodynamic function called the thermodynamic potential. For microcanonical ensemble, thermodynamic potential is entropy. For the canonical ensemble, fortunately for us, that becomes the Helmholtz free energy, which is one of the very important things. Why Helmholtz free energy is so important? Because Helmholtz free energy, taking derivative of Helmholtz free energy, you get most of the quantities. Like take the derivative of Helmholtz free energy with temperature, you get the entropy. Take with respect to volume, you get the pressure. So this is the beauty of Helmholtz free energy. That's why canonical ensemble is theoreticians' favorite, and we do much of our work in the canonical ensemble. Even much of simulations are also done in canonical ensemble. Okay. Now we have to maximize that, but with these two constraints. Okay. That means I cannot just do it blindly. Now there is a method of doing called method of constant variation, which is also called method of Lagrangian multiplier. Have you done that? Thermodynamics, sometime there is a formulation called Legendre transformation and all these things. there's a beautiful thermodynamic formulation which we are taught. That's a new nice thing we learned in our first course. That is called Cara-Theodori and all these things. So you guys have not done that. Okay. Cara-Theodori formulation should have been taught in integrated PhD at least. Okay. If not, let me see. So these are the two conditions which I have to satisfy. So my distribution, which is here, has to be I need to find the extremum with this, and I told you the way it is done is the method of the Lagrangian multiplier. So basic idea is that I want to get an extremum, which is a minimum, and that has to be constrained. That means that minimum cannot be any. If I just go ahead and did the extremum of that, I'll just find everything every NJ equal to constant. That's the value it will come out, which is the microcanonical. But now we have to do it with respect to this constraint, because we are allowing the fluctuations in energy, and each system has a different, and we have to find the distribution. The distribution is not constant. So with this thing, that the way that is done is the method of Lagrangian multiplier. I will probably send you some link and document with that. So this is the quantity that we are going to, I just wrote there, and then one can say, okay, just one of you asked that the most important thing now is for me is to get the probability of being in energy level J, and this is the probability energy level J, which you already know there is a distribution, and you know what will come out also, which one distribution. Okay, but now we are doing it exactly. So this is okay. That how to get a probability of a system being in energy level J is number of them in energy level J, omega for given that particular distribution which is here, and then I normalize it. This fine? Okay. Then please read this writing that is here. So this microscopic derivation of Boltzmann distribution. So I have to take the log of that, but I have to take that with this thing. We have to do that with the method of constraint, and that requires that the quantity ln omega to be modified by that. Now look at this expression. This is the method of constant variation, Lagrangian multiplier, very useful and very profound method of mathematics, used repeatedly in mathematical physics and in physics and chemistry. Now look at that. I want, in my variation of ln omega j, two conditions which are constant. One is NJ. Now, this, when it goes and hits there, this automatically goes to 0 because this is constant. Okay? Now, this goes and hits there, and again that goes to 0. Okay? Now, this exercise allows me to pick now. So, this omega NJ I have done there. I have added these two conditions in order to make sure that I don't pick up any rubbish distribution. I pick up that distribution which obeys this condition. So I introduce that condition into these things. This is the method of Lagrangian multiplier. Okay. Now you will find there's one of the better places is the person who developed Mathematica is called Wolfram. Wolfram has a WALFRM, very famous guy. He was a Caltech professor at the age of 21. He's genius, prodigy, who did many things. One of the things, he has an encyclopedia of mathematics. And Wolfram has a tiny little derivation of the Lagrangian multiplier. Usually going to Wikipedia you should know are written essentially by school and college kids. So they are not very useful much of the time, and sometimes wrong. But Wolfram will not be, written by mathematicians. Okay. So these now we have to evaluate. Now how do I do that? I just evaluate that. So what I have to here, I have to go back and use ln omega that I just derived upstairs, and then I take the derivation. When I take the derivation and I do like Starling's approximation, the one that I have just done above, so I get this equation. Is that okay? So one has used this one.
Sir. So what is alpha, beta?
Alpha,
I do
beta
not follow.
are the constants. So what one is doing, these are constants, they do not depend on nj. So these are added to as a method of constant variation. So we are going to do a calculus of variation. Okay. That means we are going to find a extremum. But the variation that I am going to do is constrained by these conditions. So this is added to this one, but is added with a constant alpha and beta. So now if I do the derivative, see, so basic idea will be now to find alpha and beta from this condition. So you have to read the method of, okay, I already explained it once and I'll go and explain it again. Okay. All right. Okay. Let me try once more. Okay. Now, so I have a condition which is omega, which is the number of ways I can distribute my particles into different energy levels. I have the condition, the total energy of my super system is constant. Total number of system in my super, because I have made a microcanonical out of these many canonical ensembles. So those two conditions I have to now put in. Now, those conditions tell me that the total number of energy is conserved in my microcanonical supersystem, and total number of particles in my microcanonical supersystem is constant. That allows me now to evaluate this quantity meaningfully, because in microcanonical they are all equally likely. So I have to pick up from these. But however, this my distribution in a microcanonical system with this constant these and these is equally likely, but they are so I can take an extremum of the distribution, but I must put the constraint that total energy is conserved, and the total number of particles is conserved, so that I have an NVE ensemble. These two conditions ensure that I cannot have any arbitrary distribution. Okay. I don't think anywhere else you will find more than that. Rest, I think you have to convince yourself. This is the method of Lagrangian multiplier, and this is the way it is implemented. It is a very standard method, which you have been taught, but it's not taught. You have to read it and find it. But I think I have done as much as I could do. Okay. And this is I told you, it's a very important technique of mathematics, or calculus of variation. And as I explained to you, this ensures that this thing is 0. This ensures this thing is 0. So this ensures that these are constant. Okay. Now, I take the derivative. And before, what I was doing before, so alpha and beta are called undetermined coefficients. In method of Lagrangian multiplier, they are called undetermined coefficients. Okay. See, I can understand you are not doing Lagrangian multiplier, but I do not accept your inability to understand basic. That I think is very clearly tells a lack of basic mathematical aptitude. And that develops when mathematics is not taught by a mathematician. You must be taking a lot of mathematics course, particularly those who do physical chemistry. And if one or two of you do theory, better be ready. Of course, I think my very statement will drive most of you away from theory. But anyway, so what I was saying, I forgot completely. Okay. now let us continue with this now. So before that, I showed you the Starling's approximation. Starling's approximation, you know, na? Okay. So this comes from Starling approximation. That you understand, right? You don't understand that. Okay. See, I cannot put with everything. So I describe that, then I take log of that, then I make Starling's approximation, and I get this thing. Okay. Is it clear? ln n factorial is n ln n minus n. Then this is the, and I again explained at length, and this is the essence and crux of a very important method of mathematical physics, Lagrangian method of multiplier, and that you go and read. I'll send you some more. But when I take the derivative, I these things, and this is called, now I remember what is this. Many methods. This is one of the methods of huge method of computer simulation. Method of constant variation. I'll take it up with integrated case if we go like maths will be taught by mathematicians. Well, but they have to do a good job, of course. I was taught by a great mathematician called Larry Sirovich. He's still in Rockefeller, 88 years old. He was himself a very distinguished mathematician. Then by Infanto, he's a very famous figure. Okay, method of constant variation. This is also called method of Lagrangian multiplier. They are classed by themselves. Lagrangian multiplier. Then there is also called method of undetermined coefficients. If you have to do any well in your life in research, don't expect too much confidence. Then you will go nowhere. Okay. So method of undetermined multiplier or undetermined coefficients. So alpha and beta are these undetermined coefficients that we introduced here. So the whole goal is to now do the constant variation, which is here. This is the constant variation, right? So this is variation and this is the constraint. So this is called constant variation. This is universal. This is the method applies everywhere in the world. When I am variation with the constraint, I put the constraint here and put the undetermined undetermined coefficients and take this thing. You can think about it very easily. You will be able to convince yourself. Just it is new to you. And then I do the Starling's approximation, and I get this. And take the derivative, I get this. Do that yourself. Put the ln omega there, and do it, and you will get that. That coefficient here. This, of course, is dnj goes. That's one of them. For example, I take ddn1. Then take ddn2. If I take ddn1, then only one survives here. That is n1, right? And then that will give alpha. Okay? If I do n1, then only one survives there. That will be here beta of that one. Is that okay? Just write it out. If you cannot do n1, n2, n3, then do the derivation and you will know. And do that Lagrange multiplier there. You take the derivative, you will get this thing. Alright? Now do that, and I'll go slow. Okay. If I do this now I can solve this. Okay. This quantity, what is this quantity? This is just total number of particles in the system. Total number of systems in my super system. So that is becomes a normalization. So then I get e to the power minus alpha x square beta ej. So equation I have not determined anything yet. Wow, this is becoming thinner. So 5.18 is so from this one taking this just exponentiating, I get this quantity 5.19. Now I have still not determined. So I have got my distribution, but in terms of my two undetermined coefficient. Now I do something interesting. This is the reason I don't want to teach from my book. Okay. I add it up. This actually should be italics n. Total number of systems in my system. Some of this has to be corrected next session. Okay. So now I add it up, and then I get, if we were alpha, I get it is no sum here, there is a sum here, that is this, and this become 1. I bring it on that side, 1 by 2 minus alpha becomes e to the power alpha. So I get immediately one condition for my undetermined coefficient alpha is e to the power alpha is e to the power minus beta. Is that okay? All right. Now, so this quantity on the right hand side becomes the, okay, now I go and go back my Pj, Nj by n, e to the power minus beta Ej Nv by minus Eta Ej Nv. This n different from that n. This n is my microcanonical. This one is my canonical ensemble n. This italic should be an italicized n, which is the total n is a. The total number of systems in my super system. However, this is not necessary, this is not required anymore. What I require is the probability Pj is this thing. So now you see this beautiful sum, which is now sum of the energy levels of my system, my own system, which I start with. This is a very neat and simple expression. These I corrected once. I don't know how it. Okay. So now let me write down this Pj e to the power minus beta Ej. Now this beautiful equation has nothing of my ensemble. All it has in it and N, V, you can have T there also, and so this Ej are the energy levels. These are the energy levels of my system. NVT system. Okay. And this is nothing but this is the Boltzmann distribution. Now what we will do, we will show that this beta is indeed 1 over kVt. Is a very famous notation all over statistical mechanics. Beta is used as 1 over kVt. And this is the one which is the partition function of canonical ensemble, log of which gives the homogenic energy. So all my ensemble discussion and description is not at the end of the day. This is a very non-trivial expression obtained at great deal of work and great deal of brilliant thinking by William Gibbs. And then we'll show in the next class how I have to go run to a place today, how this beta becomes 1 over kVt and log of that becomes partition function. This becomes partition function, log of that gives the homogeneity. Then what we call a realization of promises of statistical mechanics, that it gives you the basic. Now we have a footing. We have a footing that I have a system, NVD system. Now they are interacting with each other, like say even non-interacting particle in a box, or rigid rotator, or harmonic oscillator. All these is where I have the energy level Cj, right? And now I can calculate the partition function now. I can calculate the Q from all those systems, even non-interacting systems. I can do the ideal gas, and I can, from this partition function, I can get the free energy. From the free energy, I get all the ideal equation, PV equal to RT, CV equal to 3 by 2 R, or in solid state normal mode analysis, Dulac-Petit's law. All these things will follow beautifully without any assumption, and completely from overlap between quantum and statistical mechanics. Quantum mechanics gives me energy levels, I give you thermodynamics. Okay, that is the interaction between the two. Okay, see you guys. I have to run.